Assalamualaikum warahmatullahi wabarakatuh, and a very good day I bid to all my panels and all my viewers. My name is Muhammad Haziq bin Muhammad Haliman. I'm a student from UiTM Shah Alam. Today I'm going to presenting about the final year project 1 which I had done for this semester. My FYP topic is thermal analysis of rocket components. The supervisor which had helped me to construct this project through this semester is TS Dr. Ahmad Hussein bin Abdul Hamid, and also my co-supervisor who is Dr. Zuraida binti Saleh. Without a further ado, let's get started. So here are my agendas on this presentation, and now we'll go through the summary first. What is the aim for this project? It is to study the thermal analysis on rocket components. For this early phase, the research is focused on the rocket nozzle first. The modus operandi which I had applied on are by using SolidWorks software to perform transient thermal analysis in simulation, and also obtaining the temperature distribution on rocket nozzle wall graph from the simulation analysis. The importance of the study to ensure the strength of the nozzle wall can withstand high temperature from combustion chamber, and also reducing the rate of throat erosion. Next, moving on to the background of this research. This research has conducted the thermal analysis on the rocket nozzle. How the thermal analysis related? Within the combustion chamber of the rocket engine are combustion gases that exceed 3500 Kelvin. This is an extremely harsh environment in which most materials cannot survive for very long before losing their structural integrity. Therefore, it is critical that each component undergoes a thorough thermal analysis to ensure their survival during the firing of the engine. Some of the major components of interest are the chamber, nozzle, and injector. For this phase, the analysis focus on the rocket nozzle only. After creating the model, the results are verified by running the simulations using SolidWorks software and using its simulation tools for transient thermal analysis. Moving on to literature review. What is the standard temperature and pressure in the rocket nozzle? To sustain the rocket's efficiency, it is desirable to achieve higher temperature and pressures on combustion heat. Pros of high pressure combustion: it enables superior performance when operating, as they allow a larger and more efficient nozzle to be installed without being significantly overexpanded. However, materials on components will lose their strength when the temperature exceeded its properties limits. Rockets can fire combustion temperatures which can reach up to 3500 Kelvin or 3200 Celsius. On the other hand, the combustion chamber on rocket is commonly run at high pressure at a range of 10 to 200 bar. Commonly used materials on rocket nozzle range from graphite, tungsten, aluminum alloys, and many other combinations of materials that can withstand such high temperatures. I only took two examples of metals, which are graphite and tungsten. So from what we can observe on the graphite, final chamber pressure 660 psi, high pressure erosion rate 6.1 mils per second, total erosion 18 mils, and erosion rating only severe conditions. Meanwhile, on the tungsten, final chamber pressure exceeded only 340 psi, high pressure erosion rate 2.2 mils per second, and total erosion 48.9 mils, which is higher than the graphite total erosion, and the erosion rating is catastrophic condition. So this shows that the graphite is better than better materials which can reduce the rate of throat erosion compared to tungsten. Based on this literature review, The analysis undergone shows that the graphite nozzles perform well with the results of the least oxidizing 5600 Fahrenheit propellants, but eventually eroded sorely with other propellants. Speaking of which, what is the methods to reduce or eliminate throat erosions? Throat erosions are caused by high pressure and temperature conditions, which including convective and radiative heating of nozzle surface, gas phase oxidizing chemical species diffuse from the core flow region to the nozzle surface, and many else. These processes have a crucial effect on the erosion rate of nozzle materials. So to minimize the erosion rate of rocket nozzles, three general approaches have been found on this literature review. 1. By improving the thermochemical resistance of the nozzle materials by modifying the solid propellant formulation and the selection of nozzle material. Furthermore, I will talk about the problem statement and objectives. So the problem here is the high throat erosion rate will be affecting the nozzle if unsuitable material is used on the nozzle, and also the losing structural integrity of the material to withstand high temperature from combustion. Furthermore, commonly, throat erosion will occur as the highest pressure temperature exposed is at the throat of the nozzle and also the types of propellant used. However, the main goal of this analysis is to determine the duration of the rocket nozzle being heated up to expect it as if it can maintain its structural integrity at high temperatures, and also obtaining the temperature of distribution on the nozzle wall. Hence, the objectives which needed to be achieved on this research are to conduct thermoanalysis, which to find out the distribution of temperature on the wall of the nozzle by using SolidWorks, and the most critical part of the highest temperature exposed on the nozzle's walls. Moving on to the scopes and the limitations of the project. All in all, the thermal transient analysis on the rocket nozzle is required to analyze temperature distribution from the combustion of propellant in the nozzle wall. The assumptions made for the analysis were the heat transported from the propellant combustion gas flow to the internal wall of the nozzle by convection and radiation, which later conducted in the nozzle wall toward the outer layer without taking into account the effect of convection from the nozzle's outer wall surface to the ambient air. So the variables involved are the geometry of the rocket nozzle is 122 mm outer diameter and 230 mm length of the total part. The material used for the thermal analysis in SolidWorks is AISI 4340 steel as the casing and C graphite as the insert of the nozzle. The initial temperature was set at 3000 Kelvin at graphite insert and 0 Celsius on the whole 4340 steel casing. The simulation set for 6 seconds of combustion time with 1 second increment time. So here is the result of the design for the graphite and the casing. Moving on to methodology. The software used, which is SolidWorks, is first validated for thermal analysis on the rocket component, which is the rocket nozzle. Temperature distribution data through the nozzle wall graph is tabulated under transient thermal analysis. From the obtained graph, the data will be analyzed by determining the duration in seconds of the nozzle wall being heated up by 3000 Kelvin temperature. So here are some the equations which are proposed for the analysis, and here the estimation on the convective coefficient for the rocket nozzle. The casing should be in the condition of a smooth tube with turbulent flow. So here are the equations. Here the simulations which I had done in the SolidWorks. Oops. Okay. So here are the assembled part for the outer casing and inner graphite. first I select to conduct the study thermal, and then set the properties to transient, because I want the result for the transient, and then set the time, total time for 6 seconds and increment time for 1 second, as I mentioned before. So first set the connections for the contact set, so that the temperature will be distributed within and outer of the nozzle wall. So I'll select it as a bonded, and select the edge of the outer casing and the insert, just like that. Then set contact set again for bonded for the outer, the inner surface of outer casing, so that the temperature will be distributed well. And then set the thermal loads, which is the temperature. As I mentioned before, the initial temperature set for the casing, for the nozzle, was 0 Celsius, and the temperature for the combustion firing is 3000 Kelvin. And I set on the edge of the inner graphite as the combustion flows from the upper, and then create the mesh. Here I'm setting the finest mesh, here is the mesh, and run the study. So there are 6 steps. You can see 6 steps here, because within 6 seconds there's increment time of 1 second. Okay, so here is the result. So you can see there is a temperature variation within and outer of the nozzle. So to probe the result, just select the probe and set at location, and you can select any locations to define the temperature at each location. So here is just the example, but the result is I've took 11 locations for the inner nozzle in the insert, and here is the graph obtained after each location's temperature. It's the same way to tabulate the data for the outer casing. Just select the locations at the outer surface. So here is the initial result that we obtained. This section presents initial findings of transient thermal analysis on the rocket nozzle. The result of the temperature of the nozzle wall against time, which was determined within 6 seconds, and 11 locations were taken point on to collect the temperature variations on the graphite nozzle wall. L0 series here maintained at on 3000 Kelvin even after 6 seconds on the wall, as the location was appointed for the combustion firing where the temperature is distributed. It is concluded that the variation of temperature is decreasing within time as observed in the other locations where the temperature is distributed through the nozzle wall. The highest temperature reached 3000 Kelvin, and the inner insert nozzle still could withstand the temperature. There are still few investigations needed to be constructed on the next phase of research, which is to check the structural integrity in more detail in the future. Here is the result of the outer nozzle wall, which is the steel casing. It is observed that the highest temperature obtained from the outer wall with steel casing reached only 2891.7 Kelvin at the 6th second. This can be concluded that the casing can maintain the temperature lower even the temperature inside of the nozzle is higher at 3000 Kelvin, which is distributed through convection and radiation on the wall. The figure here showing the result from the obtained probe result on each of the locations pointed on the nozzle surface, just like I showed in the video before. So based on few literature reviews, it is stated that there were results obtained showing that the nozzle casing material had begun to lose structural integrity strength, but it happened at the end of the burning of combustion time. Hence, the nozzle structure will still can be withstanding the heat received. Nevertheless, the material structural integrity of temperature should be included in structure analysis when designing a rocket with a longer burning time in the future. And for the next research, the targeted component will be the body of the rocket. The material used on rocket nozzle thus withstand high temperature from combustion even after burning time. For the last slide, here is the Gantt chart, which is the flow of the project on this semester. Also included the plans for FYP2 in the next semester. With that, thank you.